On a starless night in the emptiest corner of the sky, telescope peers into the past. The image on the screen is not just a picture, it's a portal into cosmic history. Amid the darkness shines a dense tapestry of galaxies, some nearby, many distant, and some so far away that their light began its journey when the universe was just being born. At the center, we see a colossal cluster of galaxies, its core a bright elliptical glow surrounded by a swarm of smaller galaxies. Curved streaks of light arc around the cluster's edges like ghostly flares. These distorted arcs are not artifacts or nebulas. They're warped images of ancient galaxies that lie much farther away. These are faint galaxies from the distant past of the universe. Each tiny dot and arc in this image is a time capsule, preserving light from billions of years ago, when the very first stars were just igniting. And today, we'll talk about the full power of the James Webb Space Telescope, specifically how it managed to collect such ancient light and reveal the dawn of time. How was this window into the past created? To obtain this image, JWST fixed its gaze on a single target for an astonishing 120 hours. That's 5 continuous days of observing the same patch of the sky. Using its near-infrared camera, NIRCam, Webb took 9 separate images using different filters in the near-infrared spectrum, each tuned to a specific wavelength of light. By combining these images, astronomers created a rich composite that spans a wide band of the infrared spectrum. Each filter adds a layer of information from shorter wavelengths just beyond visible red light to longer ones that reveal the faintest and reddest objects. Why infrared? When light travels from the most distant galaxies, the expansion of the universe stretches it into infrared wavelengths. James Webb was designed for exactly this. Its 21-foot mirror and sensitive detectors are optimized to collect this stretched ancient light. In just 12.5 hours of exposure, the telescope's infrared vision already surpassed what the Hubble Space Telescope achieved over several weeks of deep imaging. Now think about the 120 hours. This image represents humanity's deepest ever look at a single target, a new record in our quest to observe the faintest galaxies. Long exposures work like time machines, gathering photons that have traveled across centuries. Faint smudges invisible in shorter observations now materialize into distinct galaxies. Each additional wavelength range helps distinguish galaxy colors, which hint at their distance and age. The reddest spots are often the oldest and most remote. Let's take a closer look at the image. At the center of this cosmic canvas is Abell S1063, a mega-monster galaxy cluster. This giant, located about 4.5 billion light-years from Earth, plays a special role. It's not just another object in the frame, it's a natural magnifying glass. The combined mass of S1063, the gravity of hundreds of galaxies and dark matter, warps the fabric of space around it. When light from galaxies far beyond the cluster passes nearby, it bends, much like light through a glass lens. The result? We see distant galaxies as stretched arcs and smeared streaks surrounding the cluster. These red-tinted curved arcs encircling the glow of the cluster are not physically part of S1063. They are magnified images of galaxies billions of light-years behind it. Gravitational lensing is the term for this phenomenon. Unlike a simple glass lens with one focal point, a gravitational lens has a focal plane or line. Background galaxies that align just right smear into rings or arcs around the cluster's center. Sometimes light from a single distant galaxy takes multiple paths around the cluster, appearing as several arc-like images in different positions. The glowing arcs in this image are perfect examples. Essentially, they are cosmic mirages formed by gravity itself. Thanks to their brightness and magnification, Webb can observe details in these incredibly distant galaxies that would otherwise be far too faint to detect. By studying these warp shapes, scientists can even determine the mass of the cluster and sometimes reconstruct what the original distant galaxies looked like. It's important to understand that these arcs show us galaxies from the infancy of the universe, located possibly tens of billions of light years behind the cluster. In some cases, the light we're seeing left its stars over 13 billion years ago. So by observing these arcs, we're actually looking at the universe when it was only a few 100 million years old. Thus, by using this cosmic lens, astronomers are doing precisely what was envisioned years ago as part of the Hubble Frontier Fields program. By the way, it's worth noting that this revolutionary deep field didn't appear overnight. It became the latest chapter in a story that began decades ago with a bold experiment, the Hubble Deep Field. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky near the Big Dipper for 10 days. Many feared it would yield nothing. But as a result of this long exposure, thousands of previously unseen galaxies emerged, glowing in the darkness, a mesmerizing variety of spirals, ellipses, and oddities on a patch of sky the size of a grain of sand held at arm's length. It was a revolutionary moment, humanity's first deep-core sample of the distant universe. In 2004 came the Hubble Ultra Deep Field, pushing the boundaries even further, followed later by the Extreme Deep Field. With each step, exposure times increased and instruments improved, and that allowed astronomers to observe fainter and more distant objects. These images, produced from days and weeks of observation, peeled back layers of cosmic time, revealing galaxies as they appeared billions of years ago. But even Hubble had its limits. With a 6-foot mirror and a focus on optical light, it simply couldn't see the most distant galaxies. As redshift approaches 10, about 500 million years after the Big Bang, Hubble's view fades. The distant ultraviolet light from young galaxies is shifted into the infrared, a wavelength range Hubble isn't well equipped to observe. Astronomers knew that to go further, they would need a bigger eye, one tuned to the infrared range. Enter the James Webb Space Telescope, built precisely to conquer this challenge. With a light-collecting area 6 times larger than its predecessor and instruments sensitive to wavelengths up to 5 microns, James Webb was born to hunt the first galaxies. Right at the beginning of its mission, it proved its potential. Its first public image of the galaxy cluster, SMACS 0723, captured in just 12.5 hours of exposure, revealed some of the faintest infrared objects ever observed, outperforming Hubble's deepest efforts, which took weeks. Suddenly, galaxies that had never been seen before came into view. In its early observations, JWST detected an unexpectedly large number of bright, high redshift galaxies, hinting that the early universe was richer and more complex than previously imagined. We should also mention the Hubble Frontier Fields program from 2013 to 2017. It paved the way for JWST's lensing method. At the time, Hubble targeted 6 massive clusters, including Abell S1063 itself, using long exposures and natural gravitational lensing to see deeper than ever before. Each frontier field combined data from Hubble and the Spitzer Space Telescope to reveal galaxies more than 10 billion light-years away. Some of these galaxies were magnified by up to 100 times thanks to cluster lensing. These images told us about the colors and shapes of early galaxies and even gave hints about the distribution of dark matter in the lensing clusters. Now, Webb, equipped with far greater power, is expanding this legacy. The deep field of Abell S1063, part of the New Glimpse program, is the spiritual successor of the frontier fields. But thanks to Webb's sharper vision, it can peer further into the past. Webb's data indicates that galaxies appeared as early as 200 million years after the Big Bang, an era entirely out of reach for previous telescopes. However, the research has also revealed surprises that challenge what we thought we knew. But more on that later. Alongside Abell S1063, Webb launched its own wide-field Cosmos Webb program, aiming to map a seemingly empty region in the constellation Sextans. From January 2023 to January 2024, Webb made 152 visits, collecting a total of 255 hours of NIRCam exposure on a miniature area of just 0.6 square degrees, along with parallel MIRI observations, together creating the largest continuous infrared mosaic ever made. In early June of 2025, the Cosmos collaboration released the processed data, and the public discovered nearly 800,000 galaxies, spanning from 3 to over 13 billion years in age, all displayed on a single interactive map. Early analysis have already revealed faint overdensities and new lensing arcs from previously unidentified foreground groups, and the number of galaxies observed is nearly 10 times what Hubble-based models predicted for comparable depths. We mentioned a few surprises that accompanied all of this. Among the most astonishing recent discoveries are several tiny red dots in Webb's images that have made scientists double down on their investigations. Scattered throughout the deep field data are several candidate galaxies with extremely high redshifts of around 16 to 18. In simple terms, these are galaxies that existed only 250 to 300 million years after the Big Bang. That's practically newborns on the cosmic scale. Discovering them is like finding traces of the universe's creation itself. But there's a mystery. These infant galaxies don't appear as small and dim as expected. In fact, they glow with ultraviolet light and have physical sizes nearly comparable to much later, more mature galaxies. Data from the Glimpse survey revealed a couple of such candidates at redshift 16. After correcting for lensing magnification, each one has a radius of about 650 light-years. For reference, their UV luminosity is similar to some present-day dwarf galaxies, yet their physical size of several hundred light-years is surprisingly large for such an early object. We expected the first galaxies to be tiny building blocks, an order of magnitude smaller, struggling to form stars. But instead, here's evidence that just 400 to 500 million years after the Big Bang, some galaxies were already rapidly forming stars and spreading out across hundreds of light years. This is what's called the early growth paradox. How did these galaxies get so big and bright so fast? According to standard cosmological models, structure forms hierarchically. Small clumps gradually merge into larger ones. In the earliest universe, everything should have just been getting started. But JWST is finding more high redshift galaxies and brighter ones than anyone predicted. The overabundance of bright UV luminous galaxies beyond redshift 10 is challenging pre-JWST theories. Some researchers have even suggested our cosmology may need adjustments to account for the abundance of these large early galaxies. More likely, it points to gaps in our understanding, either in the efficiency of early star formation or in the amount of dust. Perhaps the first galaxies were especially good at turning gas into stars. Or maybe they were rich in massive stars, which made them shine unusually brightly for their mass. Glimpse results show these galaxies have blue UV slopes, indicating very little dust and extremely young stars. In essence, they are pristine star factories. Moreover, their number density, the quantity of such galaxies in a given volume, is higher than expected, continuing a trend seen in galaxies with lower redshifts. In other words, a lot of stars in the universe form very early on. Imagine a galaxy perhaps 1 billion times less massive than the Milky Way, but furiously forming new stars in a region only a few hundred light years wide. That's what the James Webb data suggest. And while these galaxies are tiny by today's standards, for their era they were exceptionally large. They could be the seeds from which larger galaxies later grew, or siblings of galaxies that later merged to form ones like our own. In any case, discovering galaxies at such high redshifts means the timeline of galaxy formation may need to be pushed earlier. The infant universe grew up fast. And clearly, these early galaxies had help, maybe through mergers, inflows of fresh gas, or clumps of dark matter that formed earlier than we thought. As one study notes, nothing in the data yet breaks cosmology. These galaxies could evolve into bright objects within the lambda CDM framework, but they certainly expand our perspective. The early universe, it seems, may have been a more fertile nursery than we previously believed. It's also worth talking about a time in the early universe when the light was on but the room was still foggy. After the afterglow of the Big Bang faded, the universe entered what we call the cosmic dark ages, a time when no stars yet existed. Eventually, the first generations of stars and galaxies formed and began emitting high-energy light. This ultraviolet radiation was powerful enough to ionize hydrogen, to knock electrons off hydrogen atoms. When that happened, the pervasive hydrogen fog that filled the cosmos, neutral and impassable to UV light, turned and ionized transparent plasma. This great transformation is known as the epoch of reionization, when the universe went from murky to clear, allowing light to travel freely. It likely ended about 1 billion years after the Big Bang, having begun a few hundred million years earlier. One of Webb's core scientific goals is to identify the sources of reionization. In other words, who turned on the light and cleared the fog? The main suspects have always been galaxies, but which ones? Early on, some thought it might have been a rare quasar or supermassive black holes in active galaxies, but there simply weren't enough of them at first. For a long time, astronomers suspected it was myriads of tiny, faint galaxies, each contributing a bit of UV radiation, together ionizing the universe. Now, JWST is providing evidence to support that idea. The Glimpse program is specifically designed to hunt for reionization sources among the galaxies it finds. Looking through gravitational lenses into the cosmic dawn, JWST can detect many faint galaxies that Hubble never could, exactly the kind that might have been numerous enough to reionize the universe. Early results show that at redshifts between 10 and 15, the number of bright galaxies drops off, while the number of faint galaxies increases significantly. These countless dwarf galaxies, though dim individually, could together produce a flood of ultraviolet photons, enough to ionize the intergalactic hydrogen. In one recent discovery, astronomers identified a compact galaxy at redshift 7 with an extremely hot, massive stellar population and very little dust. The kind of galaxy capable of emitting large amounts of ionizing radiation. Essentially, it's a perfect reionization factory. Multiply that by thousands of such faint galaxies, and you have strong evidence that they collectively ended the cosmic dark ages. Meanwhile, programs like GLIMPSE are studying whether enough of these faint galaxies existed at even higher redshifts, beyond 10, to get the job started even earlier. So far, the early signs are very promising. As we gaze into these infant galaxies, another question arises. What were they made of? The very first generations of stars were born in primordial simplicity, composed almost entirely of hydrogen and helium forged in the Big Bang, with virtually no heavy elements. And yet the galaxies Webb is finding, even just 200 to 300 million years after the Big Bang, already show signs of chemical evolution. When JWST splits the light from these distant objects using its spectrograph, it detects the fingerprints of heavy elements, glowing emission lines from atoms like oxygen, neon, and nitrogen in the gas surrounding young stars. In astronomy, these are called metals, elements heavier than helium, and they cannot be made in the Big Bang. They are forged inside stars. Every atom of oxygen in the universe, for example, was synthesized in the core of a massive star or during a supernova explosion. So when we find oxygen in a galaxy that existed 600 million years after the Big Bang, it means stars had already lived and died. At least one earlier generation must have created and dispersed those atoms. Recently, JWST observed a tiny galaxy called Excels 63107 at a redshift of 8.3, just 600 million years post-Big Bang, and found it to be extremely metal poor, effectively a time capsule of an early star formation. Its oxygen content is only 1.6% that of our Sun, one of the lowest metallicities ever observed. And yet those meager percentages speak volumes. They tell us that some stars had already existed there and seeded the galaxy with a sprinkle of oxygen. Excels 63107 resembles a second-generation galaxy, among the most primitive we've discovered, but not completely untouched. Its spectrum reveals a bright emission line of nitrogen-3 from doubly ionized oxygen and even neon-3 from neon, signs of active, massive stars energizing the surrounding gas. The measured oxygen content confirms this galaxy holds only about 1/60th of the heavy element enrichment seen in our solar neighborhood. For reference, typical modern galaxies are far more enriched, and our Sun itself is the product of billions of years of stellar generations. What Webb has found is essentially a fossil galaxy, still running on cosmic fumes, practically on primordial gas, but just tainted enough to prove that even by then, stellar furnaces were already blazing. In fact, earlier JWST observations had already hinted that many high redshift galaxies were somewhat rich in metals. Finding elements like carbon, oxygen, and nitrogen in galaxies at redshifts 8 through 10 led astronomers to conclude that the first population 3 stars may have formed and exploded very rapidly, enriching their surroundings in record time. So what does all of this tell us? In one deep image, in a single 120-hour gaze, JWST has captured a cosmic saga. We see a cluster acting as a cosmic lens, countless galaxies scattered across space and time, evidence of rapid galactic growth, hints of the first cosmic dawn that ended the Dark Ages, and faint chemical signatures of the earliest stars enriching the primordial universe. Each arc of light in this image is a fragment of an epic puzzle. How did the universe evolve from darkness to the vast diversity of stars and galaxies we see today? And Webb is helping us piece that puzzle together. It has shown us galaxies that, against all odds, flared to life within just 300 million years of creation. It has shown that even the smallest galaxies can have an enormous impact, collectively lighting up the cosmos. And in the rare metals glimmering in the glow of cosmic dawn, we trace the echoes of the first supernovae. When we look at a deep field, we're not just looking into space. We are looking through time, becoming witnesses to ancient stories written in life itself. When and how did the first galaxies form? What were they like? How did cosmic night give way to light? The answers to these questions are only just beginning to emerge into our focus, faintly glowing from the depths of time. Casting a glance into the infancy of the universe, just 500 million years after the Big Bang, astronomers discovered an incredible object. A tiny crimson galaxy, barely visible in JWST images, hides a colossal black hole in its core. How can an object of such mass have formed so quickly when the universe was less than 500 million years old? Designation: Capers, LRD Z9. The light of this galaxy began its journey 13.3 billion years ago. Its spectrum shows gas rotating at about 2,200 miles per second around a central mass. Today we'll explore how JWST was able to detect the presence of the earliest black hole in such a tiny distant galaxy. We'll witness astronomers push the limits of current models to confirm the existence of this object, and why all these numbers challenge standard theories of black hole growth. Let's begin with the fact that at 3% of the current age of the universe, about 500 million years after the Big Bang, space was in a stage of cosmic dawn. Stars and galaxies were just beginning to ignite, and the epoch of reionization, when the first starlight reionized hydrogen gas in space, was underway. Until recently, the most distant confirmed galaxy was GNZ11, discovered by the Hubble telescope and dated to about 400 million years after the Big Bang. While astronomers were amazed by the sheer distance between us and GNZ11, it showed no obvious signs of a black hole. It appeared to be a young galaxy with explosive star formation powered by newborn stars. And then JWST took the stage. A revolutionary infrared observatory launched in 2021. JWST was designed to peer deeper into infrared light than the Hubble telescope and see the first light of the universe. The light of distant galaxies is stretched out, shifting into the red and infrared wavelengths as a result of the expansion of the universe. Thanks to its large segmented mirror and sensitive instruments, James Webb Space Telescope can capture images of these primordial galaxies, as well as analyze their light using spectroscopic. The ability is crucial. While Hubble could photograph such galaxies, JWST spectrographs can decode the actual light, revealing the chemical composition, distances to these galaxies, and even the motion of gas within them. And so astronomers move from simply observing a faint dot to truly understanding what it represents. By 2025, JWST had already identified many candidate galaxies with redshifts of 713. However, this raised a big question. Could any of them contain the seeds of the supermassive black holes seen in later epochs? Extremely bright, active black holes known as quasars were observed to exist about 700 million years after the Big Bang, which means some black holes grew rather quickly. And yet, confirming the presence of a black hole in an even earlier and smaller galaxy is extremely difficult. Although spectroscopy is the gold standard for confirming distances and detecting signs of black holes, it requires enough light and the right conditions. Most distant candidates showed no clear spectral evidence of black holes until now. So everything was set for discovery. A special JWST program called CAPERS, an anagram that stands for Candles Area Prism Epoch of Reionization Survey, was aimed at confirming the existence of the most distant galaxies and studying their properties. When JWST gathered deep images and spectra of the young universe, scientists noticed something unusual. Tiny, very red, and surprisingly bright galaxies began to appear in the data. They were unlike anything Hubble had ever seen. Researchers nicknamed them Little Red Dots, or LRDs. Having existed only within the first 1.5 billion years of cosmic history, LRDs became an intriguing mystery. What were these tiny ruby-red galaxies? Were they simply small galaxies filled with old red stars? Or could they be early galaxies lit up by active black holes? The discovery of Kuiper's LRD Z9 would soon provide a dramatic answer. In one of these surveys, PRIMER, the public release imaging for extragalactic research astronomers, first detected the object now known as Kuiper's LRD Z9. In the PRIMER field images, this object appeared as a faint red dot, intriguing enough to mark as a high redshift candidate. It was very compact in size, extremely red in color, and yet brighter than expected for such a tiny galaxy at such a great distance. These characteristics match the profile of an LRD, tiny, often just a few hundred light years across, distant and red. Yet they stand out in JWST's infrared images because they emit most of their light in red and infrared wavelengths. This could be due to color changes from dust or from starlight stretching into such long wavelengths. At first, astronomers put forward several theories about the nature of LRDs. Were they dense clusters of old stars? Could they be shredded star remnants feeding a budding black hole? Or perhaps they were exactly what they appeared, young galaxies containing fast-growing black holes. The Kuiper's program was designed to solve mysteries like this one. Using JWST's NIR spec instrument in prism mode, Kuiper's can capture spectra of many faint galaxies at once. Spectroscopy would reveal whether these candidates were truly distant and identify their internal sources of energy. And so, a team led by astronomer James Taylor and his colleagues pointed Webb's spectrograph at the red dot from PRIMER. Kuiper's LRD Z9, as it was named, did not disappoint. The prism spectrum gave a clear result. This galaxy lies at a redshift of 9.288, meaning we see it as it was about 500 million light-years after the Big Bang. This is at the very edge of JWST's reach for galaxies. It was a fantastic confirmation of distance that firmly placed Kuiper's LRD Z9 among the earliest known galaxies. However, the redshift was not the end of the story. It was only the beginning. When Taylor's team studied the details of the spectrum, they found something unusual. Among the faint light, there was a broad hydrogen emission line, specifically the hydrogen beta line, moving at thousands of miles per second. Additionally, they detected narrow emission lines from doubly ionized oxygen at specific wavelengths. This combination of a broad hydrogen beta line and narrow oxygen lines is a characteristic signature of an AGN, an active galactic nucleus. Simply put, Kuiper's LRD Z9 contains a growing supermassive black hole at its center with gas orbiting it at an incredible speed. You may wonder, how does fast-moving gas signal the presence of a black hole? Astronomers use a method similar to listening to a siren with a Doppler shift. Gas orbiting a black hole can reach an orbital speed of thousands of miles per second due to the extreme gravity of the black hole. Gas moving towards us is blue-shifted, compressed to shorter wavelengths. Gas moving away from us is red-shifted, stretched to longer wavelengths. If you have an entire ensemble of gas clouds rotating in a disk, their collective light produces a broad emission line wider than almost anything else in astronomy. There aren't many other things that create this signature, explained Dr. Taylor, and this galaxy has it. The broad hydrogen line in the spectrum of Kuiper's LRD Z9 was unmistakable. This little red dot is actually an early quasar, though a comparatively faint one, shining with the glow of its black hole. After detecting an active black hole, the team was able to measure its properties. Using the viral mass estimate method, they treated the fast-rotating gas as an indicator of the black hole's gravitational pull. A virial mass estimate means balancing kinetic and potential energy to calculate the mass required to keep the gas in orbit. From the width of the hydrogen beta line, they estimated the black hole's mass to be about 3.8 times 10 to the 7th solar masses. With a considerable margin of error, and in the most extreme probable case, the black hole's mass could be as high as about 300 million solar masses, roughly half the mass of all the stars in its galaxy. Even the conservative estimate of 35 million solar masses is striking for such an early period. For reference, the central black hole of the Milky Way has a mass of about 4 million solar masses, while the black hole of Kepler's LRDZ9 is 10 times heavier, and it only had a few 100 million years of growth. The galaxy itself, judging from the stellar spectrum, has no more than 1 billion solar masses and stars. This means that the black hole dominates the mass balance, which is rare in later cosmic history. The spectral energy distribution also showed a noticeable Balmer break, a sharp drop in light at certain wavelengths. The Balmer break often indicates a significant population of older stars or the presence of natural gas absorbing starlight. In Kepler's LRDZ9, the team found that the Balmer break is best explained by a model in which the black hole is surrounded by a layer of dense, dusty gas. This shell reddens the galaxy's light, contributing to its LRD appearance, and it possibly feeds the black hole. The little red dot was red partly because of an actively accreting black hole, a direct confirmation that at least some LRDs are powered by an active galactic nucleus. The discovery of a black hole of such high mass in a galaxy that existed only 500 million years after the Big Bang immediately raises the urgent question: how did it grow so large so quickly? According to Stephen Finkelstein, the research co-author, the detection of such a massive black hole at such an early stage of the universe, quote, adds to growing evidence that early black holes grew much faster than we thought possible, or they started out far more massive than our models predict, end quote. This is a profound cosmic mystery. According to the Standard Model, black holes form as a result of the deaths of massive stars. These light seeds may initially weigh from a few dozen to a few hundred solar masses. Given the Eddington limit, the natural maximum rate of accretion or feeding that a black hole can sustain, only a light seed black hole can grow this fast. The Eddington limit is essentially a tipping point. If a black hole accretes too quickly, the infalling gas heats up and gets pushed outward by its radiation, stopping further accretion. It's like a cosmic traffic law that has a speed limit. Accretion above the Eddington limit can happen for short periods, but it's hard to maintain for long because of the feedback that blows the gas outward. At the Eddington limited growth rate, a black hole's mass can double approximately every few tens of millions of years, starting, say, from a light seed of 100 solar masses right after the formation of the first stars. Even steady Eddington growth over 500 million years would only result in an increase of a few thousand times, perhaps to 1 million solar masses. That's still 10 to 100 times smaller than the Kepler's black hole. Thus, if our calculations rely solely on light seeds and normal growth, something doesn't add up. Either nature found a way to make black holes heavier from the very beginning, or these black holes fed at rates far above the Eddington limit. From a scientific standpoint, we may be seeing evidence of the heavy seed scenario. According to the heavy seed hypothesis, it may be possible for a black hole to form not from the collapse of a single star, but from the direct collapse of a massive gas cloud or from uncontrolled stellar mergers in a dense cluster. This could lead to the birth of the initial black hole of 1 million solar masses, far larger than any star. If the LRDZ9 black hole began its life as a heavy seed of, say, 10 to the power of 5 solar masses, then reaching 10 to the power of 8 in 500 million years would not be an extreme outcome. It could have happened even with Eddington limited growth. On the other hand, if it began as a typical light seed of 100 solar masses, it would have required super efficient accretion, multiplying its mass more than 1 million times in less than 500 million years. That likely means there were periods when it exceeded the usual accretion rate limit, consuming gas at enormous speeds or frequently merging with other black holes. Interestingly, the properties of the LRDZ9 galaxy suggest that it may not contain a huge number of stars. The stellar mass is 1 or 2 orders of magnitude lower than the upper mass of the black hole. This may mean that the galaxy funneled most of its gas early into the black hole rather than star formation. It's like a cosmic trade-off, to grow the stars of the galaxy or its central black hole. Overall, this observation challenges our theoretical models, which before JWST mostly assumed the presence of relatively small black holes in such early galaxies. The first few 100 million years may have been a more favorable environment for black holes than expected, or perhaps there were special conditions that allowed these giants to flare up and inflate rapidly. How does this discovery relate to the famous GNZ11? GNZ11 used to be the record holder as the farthest known galaxy, first discovered by Hubble and later confirmed by JWST as lying at a redshift of 10.6. It appears as a bright but relatively small galaxy, observed as it was only 430 million years after the Big Bang. The light of GNZ11 is dominated by stellar emission, basically a stellar baby boom. Surveys conducted by JWST showed that it is a massive, compact galaxy with star formation and low metallicity, which, given its early epoch, produces stars at an extraordinary rate. There were no obvious signs of an active black hole discovered in this galaxy. Its spectrum looks more like a galaxy within nebular emission lines from hot young stars rather than a quasar. If there is a black hole present, it may be relatively modest or quiet compared to the bright light of star formation. In contrast, Kuiper's LRDZ9 is about 100 million years younger than GNZ11, meaning closer to us on the cosmic timeline, but with a fundamentally different power source, an AGN. If the brightness of GNZ11 is likely due to millions of young stars, then the luminosity of LRDZ9, especially in the infrared range, is boosted by accretion onto its black hole. This difference is crucial because it tells astronomers that the early universe was already quite diverse. It is also notable that LRDZ9 is extremely compact in size, even compared to GNZ11. LRDZ9 is described as having an effective radius of a few hundred parsecs, a truly tiny system. Its diminutive size likely helped its black hole dominate, since gas in such a small galaxy can flow to the center more easily. However, even while LRDZ9 was being studied, another JWST discovery began offering clues about how such a heavy black hole could have formed so early. Meet the Infinity Galaxy, named for its unusual shape which resembles the infinity symbol. Discovered during the Cosmos Webb survey by researchers Peter van Dokkum and Gabriel Brammer, this system appears to be the result of a head-on collision between two disk galaxies. James Webb images show two overlapping reddish rings of stars, the remnants of the two galaxies. Each of the original galaxies still has its own nucleus, but surprisingly, between these two nuclei in the overlapping region of debris and gas, JWST and follow-up observations have found signs of a third black hole not tied to the center of either galaxy. This rogue black hole in the middle of the collision has a mass of about 1 million solar masses. What's it doing here? Van Dokkum and his team proposed a revolutionary idea that this black hole formed in place at the collision site as a result of a direct collapse of a gas cloud. Essentially, when the two galaxies collided, their gas was shocked and compressed in the impact zone between them. Instead of triggering a burst of stars, one specially dense knot of gas collapsed directly into a black hole, skipping the usual stellar phase. This newborn black hole is not located in either galactic nucleus. It hangs in a no-man's land between the galaxies, feeding on gas from the debris of the collision. X-ray and radio observations with NASA's Chandra Observatory and the VLA confirm that this black hole is active and accreting. Why is Infinity Galaxy relevant to Kepler's LRDZ9? It provides proof of concept for the heavy seed scenario. Here we have a modern example. Since Infinity Galaxy is not as far away as LRDZ9, therefore we witness it later on the cosmic timeline. In this case, the black hole seems to have formed directly at a mass of about 10 to the 6 solar masses, exactly the kind of jumpstart mass that early universe black holes might have required. Van Dokkum explained the broader context. Traditionally, there are two main ideas for how black holes are born. There's the light seed path. Many small black holes form from dying stars, then merge and accrete to grow larger. But this takes time, possibly too much time for the giants of the early universe. Then there's the heavy seed path. One direct collapse forms a black hole with a mass of 1 million solar masses all at once, which can then grow rapidly. Infinity Galaxy seems to lean toward the heavy seed explanation. If this process can happen due to a galaxy collision, then in the very early universe, protogalactic conditions such as rapidly collapsing primordial gas clouds under special circumstances could similarly produce massive seeds. The existence of LRDZ9 suggests that something like this may have taken place. Its black hole may have started as a heavy seed formed by direct collapse in the core of its progenitor galaxy, perhaps aided by the fact that it was very small and gas-rich. Alternatively, it may have started as a stellar mass seed, but then undergone periods of super-Eddington accretion. Infinity Galaxy demonstrates that nature can create black holes in unusual ways when the circumstances allow. In the case of Infinity Galaxy, the trigger was a collision. In the case of Kepler's LRDZ9, the trigger may have been the rapid early collapse of gas in a newborn galaxy, perhaps a collapse facilitated by factors such as low angular momentum of inflowing gas that did not fragment into stars. One way or another, heavy seeds are increasingly becoming the preferred explanation for the JWST discoveries of many supermassive black holes in the first 5 to 10% of the cosmic timeline. So, Kepler's LRDZ9, this tiny galaxy that was just a red dot in earlier surveys, turned out to be a quasar in disguise, something we could only confirm with the spectroscopic eyes of JWST. This tells us that 500 million years after the Big Bang, the universe was not too primitive to host active galactic nuclei. In fact, these AGN may have been more common among early galaxies than we had thought. This discovery has an impact on theories of cosmic evolution. If black holes were experiencing rapid growth in those first galaxies, they could have significantly influenced their surroundings. A black hole that is consuming matter will radiate and heat gas, possibly regulating star formation. The discovery also challenges our models of black hole formation. We now have concrete data to calibrate heavy seed models or rapid growth scenarios. As more objects of this kind are discovered, we'll be able to start mapping the prevalence of supermassive black holes across different epochs and determine whether our universe required special conditions to form such monsters. All of this pushes astronomers to refine simulations of early galaxies. Can they naturally produce something like Kepler's LRDZ9? If not, then what physics is missing? Already, this has revived debates about direct collapse black holes, massive primordial stars, and exotic physics of the early universe that could have accelerated black hole growth. How many more of these ancient black holes are hiding in tiny galaxies? Did they help bring an end to the cosmic dark ages, perhaps filling their surroundings with energy? Are they rare anomalies or the tip of an iceberg that shows black holes played a fundamental role in galaxy formation from the very beginning? Our video is coming to an end, but the scientific journey is far from over. The team behind this discovery is already planning follow-up observations. spectra with higher resolution, and possibly even attempts to detect X-rays from this distant AGN. Today we're lucky to witness this story unfolding, billions of years after it began. And for now, we continue to listen with our great observatories. Who knows what cosmic dramas playing out at the dawn of the universe we will discover next.